Now, this video is about dynamics, or why things move, or rather why they change their movement. Because we've already talked about inertia and Newton's first law. Objects moving uniformly in a straight line will keep moving this way. This is the natural state of motion, what things naturally do without any exterior force acting on them. Alright, but this immediately begs the question, what if there is a force acting on them? And this is exactly what Newton's second law is all about. Forces cause accelerations. So whenever we see things speed up or slow down or change direction, we know there must be some forces at work causing these changes. And while this may sound rather unremarkable, it's actually a really big deal. It's arguably even the reason why science itself blew up the way it did. Let's start with Newton's second law in full text. The change of motion of an object is proportional to the force impressed, in the direction in which the force is impressed. The change in motion is actually a change in momentum, but for constant mass this is the well-known F equals ma. There are many ways to read this equation, but the most significant is forces cause accelerations. We have talked about velocity and acceleration already a lot in the video about kinematics, so if you need a refresher there, you might just want to check this out. Now, by definition, an acceleration is any change in velocity, meaning either speed or direction. So any motion that isn't uniform in a straight line is in fact accelerated, even if it doesn't look like it. If we rearrange F equals ma, we'll get another useful form. A equals F over m. This means two things. The stronger the force, the stronger the acceleration caused, which makes total sense. The stronger you push, the more velocity you give an object. But also the larger the mass, the smaller the acceleration caused. Which also makes total sense, because everybody knows that heavier objects are more difficult to push. With this we can also solve why all things fall equally fast. While the force of gravity is actually larger for heavier objects, the inertia of the heavier objects is also larger. So they are pulled stronger, but also have more resilience against that pull. In the end, both factors cancel out exactly and everything is accelerated the same. So let me summarize what we have learned so far. Objects moving with a constant velocity, including velocity of zero, so standing still, are just doing what things do on their own. Keep moving the same way on and on. And again, there is no need to explain this, to find a cause behind it. This is just the natural behavior of objects, and we have called it inertia. Objects that change their speed or direction are accelerated, and this acceleration must be due to some force or forces acting on it. Note that in the case of several forces acting, it may very well be that they exactly balance each other out, so no net force is acting, meaning no change in motion. So this lets us understand a lot of what was going on in the previous videos about mechanics, which is a great thing, deeper understanding. But there is more. There is one more thing, and this changes Newton's second law from a pretty regular looking formula into a complete game changer. In the video about kinematics, we saw that an object's trajectory already contains the full information about the entire motion, and we can directly derive velocity and acceleration from it. Now, the catch is, it also works in the other direction. If you know an object's acceleration, you can calculate its velocity, and from its velocity you can calculate its trajectory. So if we know the forces at work, Newton's second law tells us how to get the acceleration from that, and from the acceleration we can get to the trajectory, which is the full information about the entire motion. As an example, if you know the law for the force of gravity, you can calculate any movement caused by gravity, from a ball falling to the ground, to a planet moving in an ellipse around the sun, to Oumuamua entering our solar system, being deflected and leaving again. And this calculation is admittedly not a simple one, so you really have to learn higher mathematics for this. But the thing is, it can be done. The mathematical operation necessary in this case is called integration. I don't fully know about the education systems of other countries, but in Europe you learn integration in the last year of high school. And if you've been to high school or know somebody from high school, you know that you don't have to be a genius for it. I have actually made a video where I derived the Kepler ellipses of planets from the law of gravity, so check this out if you want to see how it works in detail. If you know the forces at work, you can calculate the complete motion of an object. It doesn't matter if it's on Earth or in the heavens or in times past or present or future. And all of this from the humble F equals ma. So arguably, with this, Newton kicked off the entire field of physics, and with it, science. There is a catch, of course. Integrating an equation is often very difficult to do, and for some equations it's not possible at all. For example, the famous three-body problem. Three objects interacting with each other through gravity. That doesn't sound complicated, but it cannot be solved in general, just for special cases. Fortunately, there is a way around this. While it may not be possible to find an exact mathematical solution, meaning we cannot write it down as a function of time, we can approximate it numerically. Both acceleration and velocity are defined as differentials, quantities that are calculated from infinitely small differences. We can approximate that by using finite differences, calculating many small steps, getting the result for the next step, and so on and so on and so on. For example, I've used Excel to approximately calculate the trajectory of a planet given the gravity of the Sun. Well, it's technically not Excel as I'm using a Mac, but it's basically the same and everybody knows what Excel is. And while this may not give us an exact solution, with enough processing power we can in principle solve any problem that we can write down. And to get a more accurate result, all we need to do is have smaller steps and more computing power. Again, you don't have to be a genius to pull this off. All I'm using here is basic arithmetic operations and spreadsheet calculation because I'm lazy and don't want to do everything by hand. And with the advent of computers, there has been a surge of new and improved numerical approximation methods. Basically, everything that is engineered, from a bridge to a car to a plane to a power plant, is engineered using such numerical methods. But in principle, any diligent person with a laptop or even just a smartphone can calculate any kind of mechanical problem, from the trajectory of the JWST to the orbit of an exoplanet. And that is Newton's true legacy. That is the key to all of mechanics.